thermal fluid sciences experts. This is Pro Ready Engineer.
Hello, this is Bassam Abdelnabi from Pro Ready Engineer. I'm excited to share a new video series featuring industry cases. If you like what you see, please consider liking and subscribing. Take care and talk to you soon.
You know, in engineering, it's often the smallest, most overlooked part that ends up causing the biggest headaches. Today, we're diving into a case study just like that, from the world of aerospace testing. It's a story about how a simple, recurring failure was more than just an annoyance. It was a massive, hidden liability. And you'll see how taking a step back to look at the whole system, well, it completely changed the game. So, let's just start with the bottom line, shall we? $375,000. I want you to just sit with that number for a second. That was the projected 10-year cost of replacing a single piece of hardware that kept failing. We're talking about what seemed like a modest component, but its constant failures were creating this huge, invisible drain on the budget. So, what was the culprit? These things called emissions rakes. You can think of them as highly specialized probes, kind of like a straw, that sample exhaust gases directly from a running jet engine so you can analyze them. The problem was, these absolutely critical probes were failing constantly. And this wasn't just a minor issue, it was putting entire high-value test programs worth tens if not hundreds of thousands of dollars, at serious risk. Right, so let's dig into this recurring, high-stakes failure. We're going to break down the ripple effect, that cascading impact that this one single underperforming component was having on everything else. So what did this actually look like for the team on the ground? Well, it was a nightmare. These rakes were only lasting for about 100 hours. And the worst part? They failed with absolutely no warning, just gone. Imagine being right in the middle of a critical engine test, and your data collection hardware just quits on you. Each test needed a set of 5 of these things, and every time one failed, the whole expensive test setup was suddenly in jeopardy. Now, the easy thing to do would have been to just find a slightly better part, right? But that's just treating the symptom, not the actual disease. To really solve this for good, we had to put on our detective hats and diagnose the fundamental root causes, the core engineering issues that were really driving this whole problem. And our diagnosis uncovered a 3-part problem. Okay, first, the obvious one. The physical durability of the rake itself was not great. But the real aha moment was the second point. It turned out the mounting structure itself was the real villain. It was creating these intense vibrations, flawed acoustic conditions that were literally shaking the component to pieces. So it wasn't just a bad part, it was a bad system. And finally, there was another big concern about data integrity. The risk that carbon monoxide, CO, was actually burning up and turning into CO2 inside the rake, which would make all the emissions data totally useless. So with that diagnosis in hand, it was crystal clear that just swapping out the part was never going to work. The real solution meant we had to step back and completely rethink the entire system, from the probe itself to how it was mounted and how the tests were run. And this slide really nails the shift in thinking. The old way of doing things was totally reactive. A part breaks, you order a new one, you wait forever for it to arrive, and you just kind of accept that your data might not be perfect. Our solution flipped that on its head. We went for a proactive redesign, applying system-level engineering, using agile manufacturing, and, this is the most important part, delivering data that had proven measurement integrity. No more guesswork. So how'd we do it? First, we tackled that vibration problem head-on by totally redesigning the mounting assembly. This made sure the test conditions were a dead ringer for what the probe would see on a real engine. Then, to handle that data integrity concern, we used Computational Fluid Dynamics, CFD. It's basically a super powerful computer simulation that let us perfect the probe's internal design to stop that unwanted CO oxidation. And finally, we leaned heavily on 3D printing for both rapid prototypes and final production. This absolutely crushed the manufacturing time, taking it from a painful 12 weeks all the way down to just 2. Of course, a fancy new design is completely worthless if you can't prove it actually works, and that the data it gives you is rock solid. So the validation stage was absolutely mission critical. We had to prove both the durability of the new hardware and the integrity of the science. And that brings us to the million-dollar question the client had from day one. Yeah, it's stronger, but is the data accurate? They were really worried that CO could still burn up inside our new probe, which would throw off all the emissions readings and make the whole thing pointless. Well, our test proved it wasn't an issue. And here's why. The exhaust gas was simply moving way too fast. It wasn't inside the hot part of the probe nearly long enough for that unwanted chemical reaction to happen. As soon as the gas sample hit the cooler part of the line, any potential reaction was just frozen in its tracks. The bottom line? Measurement integrity was proven. That huge concern was completely eliminated. Okay, so we've solved the durability, we've confirmed the data integrity. Now let's talk about the final return on investment. This is where we get to quantify the real-world business impact of applying smarter, systems-level engineering.
And this table, this really tells the whole story. I mean, look at that, a 400% increase in the rake's life. That's a direct result of fixing the acoustic problem. Now, you combine that longer life with an 80% cut in lead time, thanks to 3D printing, and that is how you get that incredible 70% cost savings over the long haul. And maybe the most important thing of all, we got a major gain in acoustic realism, which means our client is now getting far more valuable and reliable data from every single test they run.
Visually, the change is just dramatic. We're not talking about a small incremental improvement here. The difference in lifetime between the old part and the new design is a complete transformation in performance and reliability. So, let's just hammer home the final results. First up, a 5 times increase in durability. That means less downtime, fewer failures, and way more reliable testing. Next, an 80% faster manufacturing cycle. This gives the test team incredible agility. If a part ever does fail, they are not waiting 3 months for a replacement to show up. And finally, all of this adds up to a 70% reduction in the total life cycle cost of this system. It's just a crystal clear example of how putting in the smart engineering work upfront delivers massive savings down the road.
If you take one thing away from this project, let it be this philosophy. We don't just fix components, we rethink the entire system. Because that's how you turn a nagging, recurring problem into a robust, high-performance solution.
And that really brings us to the end. The key takeaway here is that sometimes the most expensive problems are the ones you've just learned to live with. By questioning those old assumptions and applying a real systems-level approach, a problem you thought was just the cost of doing business can be turned into a huge source of efficiency and savings. So the question I want to leave you with is this. What's the small, recurring failure in your operation that might be hiding a much bigger opportunity?